class, we just introduced the concept of the input power factor, that is a fundamental power factor, and how it affects the due to the firing angle. Okay. So, fully controlled converter, we said as the firing angle increase, the power factor will decrease, and for the semi converter, it is half of the firing angle. So, there is an improvement in the power factor. So, what I want to say that in all phase control converter, if the input AC current is non-sinusoidal. So, this will affect the performance of the system. Okay. So, now there is a way for assessing the performance. This is from the input power factor and the input total power factor and the input displacement factor and or the fundamental and based on that one the fundamental power factor. So, what is the let us talk about the input power factor. Input power factor. Input power factor, that is PF, is defined as mean input power or the power due to the fundamental component, that is mains is fundamental and from the non-sinusoidal current the fundamental current which is and the fundamental voltage and the power factor which is that contribute to the input power. So, we will say input fundamental power, mean power, input power, fundamental component. Divided by input RMS, input volt ampere. What is the mean input power? We know the input current is nearly for a phase control converter, fully controlled converter. For fully controlled converter, we approximated the input current nearly a square wave pulse like this. Okay, equal positive and equal negative. The fundamental component will be something like this. Okay, and because of the firing angle, this fundamental will be displaced or not in the same phase with the input mains voltage. So, what is the input power factor? That is input VRMS into I1 fundamental RMS into cos of phi. Phi is the alpha firing angle divided by input is the total input volt ampere. So, input is voltage is fundamental. So, RMS. What is the total RMS? What is mean by total RMS? Because of this of this square wave, this is an AC waveform. What is the RMS or what is the equivalent DC? So that the same square wave and the DC when pass through the same resistance, it will produce the same heat. So, in this case, if this is the value, ID is the peak value, the RMS value will be ID. So, the total RMS of the system, total RMS of the input waveform, not the fundamental, that we represent as I, not the fundamental, total RMS. Okay. Now, as the displacement or the firing angle increases, what will happen? This value will decrease, the cos alpha decrease. So, for the same power, but the power is demanded by the load, but we require voltage control. For voltage control, we are using the firing angle, that is the alpha. So, suppose we are controlling the voltage and the load requires same power. As the firing angle varies, this factor will slowly decrease. Then what happen? VRMS is fixed, the mains voltage is fixed. So, this power it will draw large and large fundamental current. Okay. So, this input power factor, this is the input power factor which is defined by this one, is a measure of the quality of the our system, power supply system. So, what we can say, for the same power, for the same output power, same output power, for the same output power, if the power factor is more, sorry, if the power factor is poor, that means this is less. As the firing angle increases, if the power factor is less, that is this portion is less or alpha is more. If the power factor, ideal power factor, we require cos alpha should be 1. So, power factor decrease, power factor is less. Hence, more current will be, for the same current, power, output power, more current will be drawn from the power supply. So, more current means more heating losses, efficiency will come down. Okay. So, even though we can control voltage through firing angle, we want to improve the power factor. The next step is improve. Ideally, we want power factor should be always unity. That means alpha should be 90, cos 90 should be, sorry, alpha should be 0. 0. So, cos 0 will be 1. That means there should not be any displacement between the fundamental mains voltage and the fundamental current. Here we said the semi-converter we can use. Semi-converter, what is the advantage? We cannot have the full output DC control, from negative to positive is not possible, 0 to positive is possible. And last class we said for the semi-converter, we have light, sorry, sorry, I will redraw again. We have upper thyristors and the bottom device are diode. Okay. So, our VAB. So, for and the load here. So, here if we draw the mains like this, we found depending on the firing angle, there is a 0 period happening. The current waveform, input current waveform is something like this. This is the firing angle alpha. This we have drawn. So, this 0 period happens when it freewheels through the thyristors and the diodes. Okay. So, the thyristor is not switched off. Why it happens? The moment this point or this point goes negative, this diode will conduct immediately. But for the thyristor to conduct, we have to give the turn on pulse. So, the moment diode comes, suppose this thyristor is conducting, now the voltage goes negative, this diode will immediately conduct this diode. If this point goes negative, that is VAB goes negative in this portion, 0 portion. Okay. Then there is a freewheel happens. So, during the freewheeling operation, the 0 period will happen. Okay. Now, here the next thyristor is fired. So, what happens? The fundamental current, if you see here, the fundamental current is here. So, the displacement between the fundamental voltage, that is V, and the fundamental current I is alpha by 2. So, alpha reduces or phi reduces, there is our power factor improvement in the power factor is there. But ideally, we want the phase control converter, fully controlled converter to get both positive as well as the negative voltage. At the same time, we want improved power factor. So, how is it possible? Now, the question is, can we run the three-phase fully controlled converter as semi-converter, positive in the positive direction as well as the negative direction? What do you mean by positive direction as well as the negative direction? Let us take the positive case. Positive case, bottom we want to work as diode. To work as diode means, thyristor, we should fire alpha is equal to 0. The moment you turn on the thyristor, it will automatically turn on. Okay. So, for that bottom thyristors, the firing angle is alpha. Let us see how we can work as the three-phase fully controlled converter as semi-converter in the forward as well as the reverse direction. So, with the firing angle alpha, the power factor is not cos alpha by 2. So, it has an improvement. Let us study that part. This is my thyristor 1, T1. This is my thyristor T2. Okay. Then T1, T2, this is T3 and T4. Okay. And here is my input voltage. Okay. Now our load. Okay. Load goes here. Now, during the positive period, that means when the output voltage varies from 0 to positive with the firing angle control, we want T4 and T3 to act as diode, so that we can give so that the firing angle to act as diode, we have to give the firing angle alpha is equal to 0 for T4 and T3. So, let us draw the sequence of operation now. This is our x axis and this is our y axis. Now, let us draw the mains voltage. This is our mains voltage, nearly sinusoidal. By practice, it is possible. Okay. This is our main. This is 0, this is pi, 2 pi and 3 pi, this goes, this is our omega t, this direction. Now, let us draw the gate pulses. Gate pulses for the G1, G2, G3. So, probably we will use this is for 1, this is the axis for 2, this is for 3 and this is for 4. So, 3 and 4 we want to work as diode. So, we will be turning on firing angle alpha is equal to 0. When this is positive, which one we should be turning on? T3 should be turning on. That means when the input is positive, the T1 and T3 should be conducting. So, T3 should be firing angle alpha is equal to 0, full positive side, this should be turned on. So, this is G3. So, we will use another color so that clarity will be better. So, this is G3. This is with respect to this period. G3 is turned on, negative side is not turned on, again positive side G3 is turned on. This is our gate pulse for is the T3. Now, for the negative side, when the voltage waveform goes negative, we want T2 and T4 to conduct, but we want T4 to act as a diode. So, that means the moment the voltage waveform this side it goes negative, this side T4 should conduct. That means at the 0 crossing we have to turn on T4. That is full negative side T4 will be turned on. So, this is T4. Now, T4 is turned on, but we want voltage control. So, voltage control is done by varying the firing angle for T1 and T2. So, let us take a typical case of firing angle alpha. So, the T1 pulse, probably here we will use a different color, so that clarity will be better. We will go back to black. So, this is the firing angle. Firing angle for a single phase converter alpha 0 starts from omega t is equal to 0, that is this point. So, this is our alpha region now from here to here, okay, alpha. T1 is fired with respect to alpha, positive side the firing angle control is for T1, and for the negative side the firing angle is for T2. So, negative side it starts from here. So, alpha is same alpha if you want to use it, this is the alpha region. Here we will assume the commutations are instantaneous, that is why at this period the one is turned on immediately, other one is turned on for making the analysis simple. This is for T1 and this is for T2. Okay. Now, for a firing angle, we are controlling the firing angle. So, for this firing angle, what will be the input current shape? What will be the input voltage wave shape? Let us see when T1 is fired. When T1 is fired and when T3 is fired, that time the input phase voltage will appear across the load. So, T1 is fired here and T3 is fired here. So, this is the only period during which T1 and T3 is fired, that is here. If you see here, during this period T1 and T3 is fired, part of the input phase voltage waveform appear across the load. So, this is T1 and T3 conducting. Okay. Now, during the negative portion, the input part of the input voltage waveform will appear across the load when T2 and T4 are conducting. So, which here which are the period durations T2 and T4 are conducting, that is from here to here. So, if you see here, that time, since it is a rectifier, even when the input is negative, see this waveform will come like this. Here we have T2 and T4. Now, if you see here, part of the waveform only coming in, there is no negative. Will there be a negative part as before phase control convert? Will not be there. Let us take this portion, when that is this portion. What happens here? During this portion, during this region, that is this region, we will mark it with a different color, so it is clarity will be better. So, during this region, the output ripple is 0. Why? If you go to the waveform during this period, that is from here to here and here to here, T1 and T4 are conducting. T1 and T4 are conducting, load is freewheeling. So, output voltage will be 0. Same way, in this period, what is happening? If you hear T2 and T3 are conducting, T2 and T3 conducting, this is the portion, it is freewheeling through this path. So, 0 will be there. So, this way output ripple will go with the firing angle, the part of the waveform, as the firing angle increases, the width of the waveform in part of the input means waveform appearing across the load will slowly reduce and the voltage will come to 0. When firing angle is 0, what happens? This portion will go here. Finally, it is kind of three-phase control rectifier. It will act as a single-phase diode rectifier. Single-phase diode rectifier with alpha is equal to 0. So, as far as the voltage waveform is concerned, we have made the converter during the positive half cycle. We have made the converter to work as a semi-converter. So, let us see the current waveform. Assume the load is highly inductive. We will say DC current is flowing through the load. So, load will always see the DC current, and the portion of the DC current will be depending on the positive cycle, it will be shifted to T1 and T3, and negative cycle T2 and T4. For freewheeling, it will go either go through T2, T3 or T1, T4. So, when T1 and T3 is turned on, T1 and T3, that is this portion. This is the input current, that is this current. If you measure, if you current probe, we connect it here, this point, the current I, input current. If we connect it here, the current waveform will be like this. Okay. During the freewheeling, that is this portion, current will be 0. Again, when T2 and T4 goes, the current direction at the input side, it goes in the reverse direction. Even though current is coming like this, now what will happen? T2 and T4, so it will go like this, come back like this. Okay. So, it will reverse. So, this is the current waveform. Now, if you see here, this waveform, input current and input voltage, where is the fundamental component? So, why we are taking the fundamental component? Input mains is fundamental voltage and fundamental current can only give real useful power to the load. Harmonics will not, with the fundamental voltage, will not give any useful power, but harmonic current, it can create losses, I square R losses in the device, it can reduce the efficiency. So, fundamental power is always fundamental RMS voltage, input RMS voltage, fundamental input current and the power factor cos phi. So, if you say what is the power factor here? So, fundamental will be symmetric about this one. So, we will draw with a different color. So, fundamental current will be approximately this way, the shape. Okay. So, if you see here the displacement, that is this one. The displacement is, if this is the firing angle alpha, the displacement is alpha by 2, alpha by 2. So, this shows during this period, during the full 0 to positive period, there is an improvement in the power factor, even though firing angle is controlled by alpha. For a for a single phase fully controlled converter, as the alpha varies, the power factor or the displacement factor is alpha. So, power factor will be, for the fundamental power factor will be cos alpha. Now, we have reduced alpha and improved the power factor, that is improved the power factor cos alpha by 2. So, there is a power factor improvement. So, quality of the power supply we are improved. Okay. It will draw less reactive power. Is cos alpha by 2, there is a sin alpha by 2 is there. VRMS, IRMS, sin alpha, that shows the indication of the reactive power drawn from the thing. So, that is reduced here. Okay. Now, as alpha varies, when alpha becomes pi by, alpha becomes pi, what will happen? Let us draw that waveform when alpha is equal to pi. Again, here alpha is equal to phi, we can draw with respect to the input sine wave. Again, we will draw, I will approximately draw the input sine wave here. This is my input sine wave. Let us draw the axis so that it will be clear. This is our x axis for the gate 1, this is for gate 2, this is for gate 3 and this is for gate 4. Now, we are increasing the firing angle alpha to control the output voltage. So, as the firing angle increases, output voltage will come down. We have derived the equation previously. It is a function of cos alpha. Now, alpha is equal to, see here during the full positive half cycle, we are not disturbing the gate pulse of T4 and T3. T4 and T3 is fully fixed. So, this is the T3 waveform. T3 waveform will be positive side, it is fully fixed. Okay. Then T3 is fixed and T4 is also fixed. So, during the full negative portion, T4 is conducting. So, this is gate pulse of T3, this is the gate pulse of T4. So, T1, sorry, this T1 I will just, so this is T1. So, if you see here, during the positive half cycle, T2 and T3 are conducting. The moment T2 and T3 are conducting means, what will happen? T2 and T3 conducts means, this is freewheeling. So, if you see here, during the freewheeling operation, if output voltage will be 0 during the freewheeling operation. So, this is the V0 part. Output voltage, that is the part of the voltage coming across the load will be 0. Again, the next half cycle you can see T1 and T4 are conducting. So, load is freewheeling. So, here also output voltage is 0. So, output voltage ripple will not come across the load. So, what it shows When the firing angle is equal to 0, alpha is equal to pi, the output voltage is equal to 0. So, we brought the varying the firing angle, we brought the output voltage waveform from positive high value to the 0 value, and every time if you see here based on the current direction here, the displacement angle is equal to alpha by 2, corresponding to the power factor will be cos alpha by 2. There is an improvement in the power factor. Now, let us take the case when the negative half cycle. Negative half cycle, if you go with the symmetry of the circuit, now you have to what we have to do? We have to fix the T1 and T3 waveform, sorry, T1 and T2 waveform, we have to fix it and only control T4 and T3. Okay. So, let us draw the waveforms during the negative half cycle. Let us go to the let us draw it negative half cycle. So, let us draw the converter waveform, converter first again. This is T1, then this is T4, let us mark T1, this is T4, this is T2 and this is T3 and the load. So, we always represent as load as motor. So, all these explanation is for drive application. So, variable voltage for DC motor drive application. This is our I input, this is our V input, AC waveform. Okay. This is our V input waveform, AC. Now, let us draw the positive and negative half cycle. Okay. So, let us first draw the sinusoidal input voltage waveform. Assuming the input is always good sine wave, but means will not be always as a perfect sine wave, but for our analysis we will assume it is sinusoidal. This is our V in input. Okay. Now, we want to vary the firing angle such that the output voltage will go towards the negative side. Okay. So, here how it is done, and as I told, here we will fix the firing angle of T1 and T2 fixed. So, let us say T1 and T2 fixed. Previously at alpha is equal to pi, there was a freewheeling. Now, on T1 and T2 is fixed. So, T1 is during the negative half cycle, T1 and T2 will act as, T1 will act as a diode. So, this is the T1 pulse. This is our T1 pulse, and the positive cycle will make T2 fixed. This is T2. Now, we are varying which are the pulses, T3 and T4 pulses, T3 and T4 pulses with firing angle, so that the output DC can go from 0 to minus negative. Let us take one firing angle, let us say this one, this is the alpha. Here after alpha we are firing T3. This is T3 gate pulse. The moment T3 is switched off, will be turning on T4. We are assuming the firings are instantaneous. So, with the moment T3 is turned off, T4 is turned on. So, this is T3 and this is T4. Okay. Now, probably we can T3 and T4 we can draw it with a different color. So, the clarity will be better. So, I will mark it with a different color. This is T3 and this is T4. Okay. Now, how the output voltage will be? If you see here, when T2 and T4 are turned on, T2 and T4 are turned on, that these are the, when T2 and T4 are turned on, that is this one, this is T4, T2, this part of the input voltage will appear across the load. So, which part is appearing across the load? T2 and T4, that is this much portion. So, what is that part? And it is appearing across the load. So, if you see negative, during the negative portions, T2 is turned on. When the input is negative, input is positive. If you see here, T2 is turned on during this portion. Hello, sorry, I made a mistake in drawing the input waveform during the negative side. So, this is wrong. It has to be, input waveform has to be on the other side. So, let me remove that one. So, I will again draw the correct input waveform for the negative side. This is the axis. So, it will be this is the waveform. Sorry, because we are going in the negative direction. So, the firing angle is this way. Already we have come to the negative side from the positive 0 side from the positive side. Now, it has to go from the negative side. That previously what we have come up to this point, negative side, alpha firing angle was pi. Now, from here you have to continue. That's it's a continuation. So, if you see here, so during this portion, T2 and T4 are conducting. T2 and T4 are conducting that part of the waveform. That waveform is already negative. So, why a negative? There was a drawing in my mistake. This is a continuation from the previous case where we are going from positive voltage to come to 0. When you come to 0, the firing angle was pi. So, and from there onwards the waveform was going towards negative side. Okay. So, that is why written this is the waveform. Now, we are varying slowly firing angle of 3 and 4. Now, during this period, start from here, from pi, now starting from pi, this is pi, this 0.5, this is 2 pi. So, we already started from 0 to pi. Now, firing angle we are slowly varying. So, if you see here, T2 and T4 are conducting. During T2 and T4 are conducting, the negative portion, that is this portion, will appear across the load, this ripple. So, the ripple voltage if you see here, it will be here. Now, again as you see here, T2 and T3 are conducting. So, it is freewheeling, that is from here to here. So, this time what will be the output voltage? Output voltage will be 0 here. So, output voltage here, this is T2 and T4 are conducting. Here it is freewheeling. So, here T2 and T3 conducts. Now, again from here to here, this portion, T1 and T3 is conducting. T1 and T3 conducts means again that part of the waveform will appear across the load. But here what are the T1 and T3 are conducting. So, again the voltage get T1 and T3 the voltage waveform comes in the negative direction. Okay. So, during this portion which are the T2 conducting T1 and T3 are conducting. This is during this portion T1 and T3 are conducting. So, T1 and T3 again it will go negative. So, this way it will go. So, negative side voltage will come across the waveform. Now, how the current waveform will be? Current waveform will be, we can draw it here. Sorry, we will draw from this point. Current waveform will be during this portion, negative portion up to this point. It will be here like this, then 0 from here to here, then positive from here to here, then again 0, then negative. It will go like this. So, this is the waveform. So, here also the fundamental will be, I will draw the different color. The fundamental will be like this. So, here also the firing the alpha by the improvement in the fundamental component is there. Okay. This way we can by appropriately giving the gate pulse alpha is 0 to thyristor, we can drive the converter in the as a semi converter in the positive as well as negative side. Now, we will study about the converter, that single phase fully controlled converter working as a semi converter in the negative voltage region, that means 0 to negative. So, again for clarity let me draw the phase control waveform. The phase control converter waveform will be here. This is again T1, this is T2, okay. This is T1, T2, this is T4 and this is T3. Okay. Then comes the load. Okay. These are input waveforms. This is our input current direction, I, E. Okay, T1, T2, T3, 4. Now, let us draw the corresponding waveform during the negative period. So, let us draw the mains waveform again from 0 to pi. This is our input mains waveform. Okay. This is axis we will draw. And let us draw the gate pulse for 1. So, here in the negative side, that is the output voltage going negative. So, here T1 and T2 will act as diode. So, during the negative half cycle, we will be fully turning on the T1. So, this is our T1. Then next is T2. During the full positive half cycle, that is here. We will be turning on T2, then here. We will assume the moment T2 is turned on, T1 will goes off, and the moment T1 is turned on, T2 will go off. Now, firing angle control is given to T4 and T3. Previously, the firing angle control was given to T1 and T2. Now, let us take a general alpha firing angle. Let us draw the waveform of gate pulse T3. A firing angle alpha, that is from here to here, firing angle alpha. This is the pulse we are given. This is for, let us draw a different color, so clarity will be better. This is our T3. T3 is given. Okay. Now, the moment T3 is turned on, we have to turn on T4. So, where is the T4 waveform? T4 waveform will be somewhere here. This is T4. Again, when T3 will, this is T3 and this is T4. Whenever T3 is turned on, T4 will be turning off. So, T4 here it will be turning on. Off. So, these are the T4, T3 waveforms. Now, with respect to this one, how the output ripple will be, voltage ripple will be. Let us draw the output voltage ripple. Output voltage ripple from here, if you see here, during the, when T2 and T3 are turned on, this is T2. When T2 and T4 are turned on, what will happen? The input ripple will come across the load. But if you see, during the positive cycle, T2 and T4 are turned on. So, the waveform will be like, it is inverter, it will happen like this. Okay. Again, when both the switches are conducting, that is from here to here, there is a 0, again it goes like this. Okay. So, this the negative ripple will come across the load. So, this continues like this. So, firing angle can be varied from alpha 0 to pi. When it comes to pi, again it will go to 0. So, how the input current will be here? Input current, we can draw it like this. We can draw it like this. When this is there, till this period, if you see, this is the current waveform. That is, when T2 and T4 are turned on, this is T2 and T4 are turned on, the current input current is in the negative direction. Then freewheeling, there is no current. During this freewheeling period, this period, T2 and T3 are conducting, so freewheeling. So, during that portion, there is no current. After that, current will again change. So, it will go like this. Again, it will come like this. So, this way we can go from negative side also. Previously, what we are varying the firing angle vary from 0 to pi. Okay. Now, during the negative half cycle, after that we will be fixing the T1 and T2 permanently, that is, it is working as a diode by keeping the firing angle alpha is equal to 0. Then to get the negative DC voltage, we are varying the firing angle of T3 and T4 with respect to the mains. So, we will get slowly firing angle when it comes to 0 to pi. At the moment here pi comes, output voltage will be 0. Then from there again when it increases, the output voltage go into the negative mode. Okay, so you get the output DC voltage like this, and we are making the converter positive and negative half cycle work as a semi converter. So here the power factor improvement is there. If you see here, this is, even though there is an alpha by 2, there is an improvement in the power factor angle is there as before the semi converter with respect to the firing. Even though alpha firing angle is alpha, the change in firing angle, there is a, if you see here, the improvement in the current input power factor is there, same like in the semi converter. Okay. So this way, this is with respect to the mains. Okay. This way we can have, there is a, not the firing angle, the output power factor is not proportional to, not decided by the alpha, it is, it's an improvement in the power factor is possible. This way I explained in the previous class for the positive side, now it is for the negative side. See here, this is for the positive side. Okay. So if you see the power factor angle, that is, it is not alpha, cos alpha by 2 here. So there is an improvement in the power factor. The same thing is achieved for the negative side also. That negative side, it is here. So this way, by controlling the firing angle or making the devices, the fully controlled converters working as in the positive and negative side, two devices as as thyristors, that means that is a full period we make it on, alpha is equal to 0 for T4 and T3 in the positive, and for the negative it is T1 and T2. We can have output DC control for positive and negative side, and improvement in the power factor is possible. Now ideal case is, ideal is the power factor irrespective of the firing angle. Firing angle is only for controlling the output voltage, but as far as the input is concerned, if you want to have efficiency, good efficiency of the system, we want the, we should draw the input mains current, that is a fundamental current with the in the same phase with the phase, that is with the unity power factor. That means the displacement angle alpha should be 0. That is the best way, that is the most efficient way of drawing power from the mains. At the same time, we require firing angle, we require a firing angle control. So this we will study in the next class using PWM operation. Okay, in the control or force commutation technique. Then after that we will come to the PWM. We will study in the next class.